I would like to rotate this curve around the x-axis, the region bounded by this curve and the x-axis. Rotate around the x-axis. I'd like you to set up that integral for me. You don't have to solve it, but set it up. First thing I do in a problem like this, draw me a picture. Find the region we're going to rotate by sketching the graph. So the region in question for our volume of revolution is this region here, which intersects the x-axis at 0 and 2. And if I'm going around the x-axis, what is the equation, the integral I get that gives me this volume? Because when I rotate this object, I'm going to get a circle whose radius is given by the height of a point on the curve, pi r squared. Perfect. I can do the integral, that's not important. What if I want to go around the y-axis? If I'm going to try and do this like we did our volumes of revolution on Friday, then I'm going to think about a slice of this region. But if I'm going around the y-axis, I should be stacking my slices along the y-axis, right? And then each slice is what shape? If I stack these slices vertically, well, it's not just one circle though. This one at the bottom is a circle, but if I pick one that's, say, a little bit higher, here's a higher y value, then I'm going to get a circle up here that's not part of the region, and then I'm going to get a circle here that is part of the region, and that is a washer shape. So the y-axis is the center of our circle. I've got the inner circle that is not part of the volume, and I've got the outer circle, which means I need an inner radius and an outer radius. I need R in and I need R out. But those radii are x values because they're measured here, horizontally. Problem. What's the equation for that curve again? And technically that's not this side, that's this side. If I want those R in and R out as x values, means I need to take this equation and write it x equals. Again, there is a way to solve cubic equations like this. I don't know it. I don't have it memorized. So I can't do that. Well, what do I do now? Okay, we're done. Goodbye. No. I could think of slicing this region up differently. Let me go back to the other picture. I had a cut straight up and down, and I knew the height of that cut. That cut had a height that was given by the y value of the equation. And down here, we're spinning around the y-axis. Artistic, I am not. Same equation. What if I take that stick, that cut we made when we're going around the x-axis? What if I spin that around the y-axis? I'm going to shape like that. This vertical line moves in a circle around the y-axis, yes? Instead of making it a line, let's make it thick, like it was one of our rectangles. Then I can picture this shape that we just made as a thin shell standing up in this shape. It's a cookie cutter. As a matter of fact, I can think of the thickness as the thickness of that little stick. That's our little dx, right? That's the thickness here. That's the width of this line. How do I figure out the volume of this piece of plastic? That would be the volume inside it, but you'll notice this is actually hollow, right? So that would give me the interior. I just want the volume of the plastic itself. Wait a minute. This is a cylinder. This is a cylinder. It's a really thin cylinder, isn't it? Ignoring the hollow inside. If I wanted the volume occupied by this piece of paper that I have rolled into a cylinder, I could unroll it and measure its volume, couldn't I? So let's take this cylinder and unroll it. And I don't want to think of the volume of a cylinder, so I'm going to change the terminology slightly. So when I think of the volume of the cylinder, I think of the pi r squared h that we were using on Friday. I'm going to think of the shell that is the outside surface, just the side, technically the lateral surface of this cylinder. Well, if I unroll it, I get the piece of paper that we made the cylinder out of, right? Now, with the actual piece of plastic, it's a little harder, but I can picture myself cutting down one side and rolling this out flat. Okay. This came from here. So this height is this height. That's given by a point on our curve. That's a y value. That's our f of x. The thickness of this slab is the thickness of that stick. That's the dx. What's this thing? What's this here? Where does that come from? From the circumference of my circle, because that's what we unroll, right? Circumference of a circle. 2 pi r. What's the radius? It's the radius up here, isn't it? So the radius in this picture is given here. Wait a second. How did we figure out where that stick was? That vertical stick there is some y value that corresponds to some x value on my curve. So this radius right here is an x value. And that means that the volume of this slab, length times width times thickness. Length times width times thickness. The circumference from my circle, the height from my f of x, and the thickness from my dx. It isn't. It should be sticking out of the page at me. So technically, I would say, oh, this is really a little thin slab. There's dx. It's the thickness of the sheet of paper. Or if you'd rather, it's the thickness of that piece of plastic. I bought a whole collection of cookie cutters. So what if I don't just use one of them, I use all of them? I could take this shape that we built here in 3D and slice it into a whole bunch of cylindrical shells. Page 461. Here is our curve, and here is our stack of cylindrical shells. And as I get more and more and more shells, I get a better and better approximation of what the volume should be. Gee, what should I do with my number of shells? I should let it go to infinity. And that turns the sum into an integral. The integral of what? That the exact expression we just came up with is the thing I'm going to integrate. So the volume by cylindrical shells can be found exactly this way. So let's do our problem. Question. Is this true for every? It's true for a decomposition of a volume by cylindrical shells. The A and the B are the regions start and end measured in radius, right? Because my X value is my radius. So I figure out what the smallest radius is, what the biggest radius is, and I integrate that. So in our reaction, in our picture, I'm going to get something that looks like this. It's a bundt cake. But I'm not slicing wedges. I don't have to deal with things sliced in wedges. I'm slicing in punched out cylinders, one inside the other. Here's a sample cylinder. We figured out the volume, go around the body. There's my height. There's my thickness. You'll notice they actually drew the little rectangle instead of drawing just a stick, so you can see the dx better. And when we unroll the slab, we see the thickness here as well. So for our problem, the smallest radius I can use is what? What's my smallest radius? Because I'm going around the y-axis, the smallest radius is here. And the largest radius is all the way out there. So the integral is from 0 to 2. And that's an integral I can do. All I have to do is multiply the x into the parentheses. 2 pi is a constant. I can pull it out front. Two x cubed minus x to the 4th dx. I haven't actually integrated yet. I just multiplied in the x. But now when I integrate, what do I get? What's my antiderivative? It's 2/4, so I might as well simplify it to 1/2 x to the 4th. Plug in 2, plug in 0, subtract, multiply by 2 pi. Put in 2. 1/2 of 16 minus 1/5 of 32. Put in 0. 1/2 of 0 minus 1/5 of 0. Wait a minute, half of 16 is just 8. I'm going to need fifths though, right? So 8 is 40 over 5 minus 32 over 5 minus 0. There's still a 2 pi on the outside here. 40 minus 32 is 8. So I get 16 pi over 5. Worked, master, it worked. Instead of thinking of my rotationally symmetric object as being sliced horizontally, I think of it as being made up of concentric vertical slices of different heights. This one doesn't go all the way to 0. But I can think of the region between these concentric rings as my cylindrical shells, which I then unfold to lay flat to get their filament. It's amazing the props you can get at the cooking center. Questions? The only reason I knew to do this, the only reason I decided to do this was when I looked at the other one and I said, if I want to do this the way we were doing it on Friday, I have a real problem in front of me. And that problem is that I don't know how to solve this equation to give me the boundaries. So the question is, can I do the algebra needed to do it the other way? And if I can, most of the time that's simple. But almost always, this is only useful going around the y-axis. Because I'm writing my functions in terms of x. Going around the x-axis is going to be easy. Going around the y-axis is going to take more work. This is easier most of the time in that case. Not always, but most of the time. For example, we did a problem on Friday. No, I mentioned the problem on Friday. I didn't actually do it. Let's consider the volume obtained by rotating the region bounded by y equals x squared and y equals x around the y-axis. First thing I want you to do, it's the same thing I wanted you to do with the problem we just finished. Draw me a picture. The region bounded by the curve y equals x squared and y equals x is this lune crescent bounded by the straight line on the top and the parabola on the bottom. They intersect at the origin, 0, 0, and at the point 1, 1. Great. Going around the y-axis. So there's my mirror image over on the second quadrant there. And we can actually do this using washers. You can. If you want to do this using washers, then you're going to integrate by stacking those washers up and down. And I can picture a little slice cut out, right? And then I've got an inner radius and an outer radius. What's the equation for the outer radius? It's y equals x squared is that curve, right? But if I'm doing the radius this way, the radius should be y goes this way. Radius should be my x value. So if I think of the radius out as being part of the curve y equals x squared, I really want to solve that for x, and I get x equals the square root of y. The inner radius. What's the inner radius? Not outer radius, inner radius. That's the short one here. So that goes to the line y equals x. Well, if it's y equals x, then it's x equals y. And the volume is the integral pi r out squared minus pi r in squared. Outside circle minus inside circle is going to give me the actual volume of the washer. dy, because the washers are stacked vertically. I need one more thing. I need limits of integration. Lowest washer gets cut at a height of y equals 0. Highest washer gets cut at a height of y equals 1. Radius out. Radius in. I can pull the pi out, it's constant, take it out front. Piece of cake. What do you get for this answer? When I put in 1, 1/2 squared is 1. 1/2 cubed is 1. When I put in 0, I get 0. So I get a half minus a third. A sixth. but I was going around the y-axis. I should be able to do this one like cylinders too. Let's picture what a cylinder is going to look like in this case. It's going to be different because this time the height of the cylinder doesn't go all the way to the ground. The cylinder itself is floating up in midair. Its height starts and ends there at each curve. Wait a second. I've got a ring floating up in the air. Doesn't go all the way. That's still fine. I can still give you the volume of this, right? What's the radius of this washer? Actually, it would just be the x, because I don't care which curve I'm going to. The radius is the same regardless of which curve I'm going to, and that's decided by which x value I picked, isn't it? So the radius is still x. What's the height of my cylinder? Top minus bottom. Just like it was between two curves, because it is between two curves. Oh. And the thickness is still dx. So the volume should be the integral 2 pi x, 2 pi r, height, thickness, from where to where? Still 0 to 1, because those are my x values for the edges. Guess what? I multiply the x into the parentheses. I take the 2 pi out front because it's constant. Do this integral and give me a number. If we don't get the same number, we done something up. Because I'm measuring the same volume two different ways, I should get the same number, regardless of which way I compute it. Guy by the name of Cavalieri in the 1700s rediscovered an idea from the Greek geometer Pappus, who said that if you have a volume, it doesn't matter how you slice it up. When you add up all the volumes of the slices, it needs to be the same. Cavalieri's principle, which is really Pappus's idea, allows me to look at shapes that are the same when I twist or rotate one into the other. As long as I can slice them into the same size slices, they have to have the same volume. Notice I get a different antiderivative because I have a different power of x than I had powers of y. I did pull out a different constant. And when I put in 1, I get 1/3 minus 1/4. When I put in 0, I get 0. What's a third minus a fourth? So I get 2 pi over 12, which is the same as pi over 6. So here's the problem. Which one was easier? That depends on you. I know a lot fewer people enjoy doing integrals in cylindrical shells. It is also a less commonly taught procedure, but a lot of people would tell me they'd rather do washers than cylinders. I disagree personally. I found this to be easier because I didn't have to rewrite stuff. But everybody's opinion varies, and if you can do it both ways, do whichever way you like. Questions? If I change my axis of rotation, I can account for that here the same way I did in my washers and in my disks method. So here's another problem. First thing you should do, draw me a picture. The graph of x minus x squared is a downward opening parabola that has intercepts on the x-axis at 0 and 1. And it says the region bounded by that parabola and y equals 0, that's the x-axis. So it's just this little piece. And I'm going to spin this around, but I'm not going to spin it around the axis. I'm going to spin it around the line x equals 2. X equals 2 is a vertical line. So I'm spinning this way. If I wanted to do this with washers, I need to write this equation x equals. I'd rather hit myself in the head with a 2x4. So let's not do that. Which means I'm going to do cylinders. So again, I say, let's picture what one of the cylinders looks like. If I can draw this cylinder, then I should be able to figure out R, H, and do my integral. So when I rotate around this line, this is going to fold over to here. And that means this point is going to end up here. And this point is going to end up here. And I'm going to have another piece of a parabola there. Let's pick any x in the original piece of the curve. This one. There's my little vertical piece that's going to be the height of my cylinder. And then that's going to roll around to here. And the top goes around. This one's a lot wider than it is tall. Okay. Height. What's the expression for the height of that cylindrical slice? That's the curve we're on, right? I'm sorry, say again? Right, but if I'm the bottom of that is the y-axis, so x minus x squared minus 0 would be correct, but subtracting 0 doesn't change squat. Radius. Radius is harder because the radius doesn't go this way, it goes there. The distance from the y-axis to this spot is exactly 2. And I moved over by x to make my slice, so the radius is 2 minus x. For what set of x values? I only choose an x in the original piece of the graph, right? It means the x has to be between 0 and 1. Now that actually means I did something different. Because I said we picked the smallest radius and then the largest radius, right? If I pick the smallest radius, that small radius is 1. The large radius is 2. What's wrong with that picture is it's going left instead of right. My dx would be backwards. So I can't do that. I need to go from left to right. So I need to write my radius as if I'm going this way. I now know everything I need to know. The volume is the integral from 0 to 1, 2 pi r h dx. Ta-da! Pappus's theorem actually says that if you know where the center of an object is, you know its area and its rotation, you can work out its volume by multiplying the path the center takes by the area. Parsley, you got a question? Okay, I said, oh, if I want to go all the way from here to here, that's a distance of 2, but I had to back up x, actually get the radius, didn't I? So 2, take away the x I backed up. Ladies and gentlemen, there are 2 important things for you to know. Thing 1, there are 2 sections of class material left. There are 5 class meetings left, 3 of which our Q&A days. You are down to the last of it. Please bring your brains back from Thanksgiving. I will see you all next week.